9, 8, 7, 6, 5, 4, 3, 2, 1. Summer! Woo! Summer!
What are we going to do with all this free time? We should go fishing.
No.
Why not? Fishing's fun. Could cook our food.
We can build a better roller coaster! Woo!
What?
But how are we going to do this? With calculus. Of course, calculus is always the answer, as Mr. Fingerhut would say.
f of x equals ax squared plus bx plus c. And two linear equations, L sub 1 of x equals L1 times x plus 0, and L sub 2 of x equals L sub 2 of x plus t. And that's, as you can see graphed over here, the two linear equations that are tangent at the points p and q on the parabolic function. And p is our origin at 0, 0, and q has a x value of 100, and we don't know its y value. Our y value will give us our elevation between p and q. So right now we have to find two equations to help find the the four unknowns given in these equations. So basically, f of x and L sub 1 of x are equal at the point px and the point py. So that means that their derivatives, the derivative of f of x and the derivative of L sub 1 of x, are both equal. We can use the same logic for L2 of x, L sub 2 of x. So basically that means that f of x and L sub 2 of x at point q of x and y are equal. Thus, the derivative of f of x and L sub 2 of x are equal. And this will help us find the equations. So right now, I'm going to find the derivatives of these functions. Okay, so these are the derivatives of the functions above. So the first derivative of f of x equals 2 times a times x plus b. The first derivative of L sub 1 of x equals L sub 1. And the first derivative of L sub 2 of x equals L2. We also know that the difference between p to q is 100 because that's q's x value. So we have q of x minus p of x equals 100, which means that q of x equals 100 plus p of x. This equation will help us find our other two equations we need to find our unknowns for the parabolic function. So now we're going to plug in the point p of x into the first derivative function of f of x in order to have our first equation. And we'll use the same method for q of x. And we're going to set this equation equal to L sub 1 because we said that the derivative of f of x and the first derivative of L sub 1 are equal to each other. So this is our first equation. Now we're going to make our second equation, which is basically going to be the same thing, but for point q of x. And we're going to set it equal to L sub 2. So now you see we have q of x right here, and before we solved for q of x, which was 100 plus p of x. So we're going to substitute that in so we have only one unknown x value, which would be p of x. Now we can distribute the 2a to 100 and p of x. As you can see, this part of the equation is exactly equal to the first derivative of p of x. So we can set this part equal to L sub 1. Now I'm going to solve to isolate our variable a. So we have an equation for a. So our first equation to find a is L sub 2 minus L sub 1 all over 200. So in order to complete this solution of a, we have to plug in the values for L sub 2 and L sub 1, which are basically their slopes, and we found that their slopes are 0.8 and negative 1.6. So I'm going to plug those into the equation to find a. Therefore, A equals negative 0.012. Since we have A's value, we can now solve for B. So we're going to use the equation of the first derivative of f p of x, which is 2 times A times p of x plus B equals L sub 1. Because we have all the unknown values except for P. So we're going to plug in A, which we said was negative 0.012, P of x, which we know is our origin, so it just equals 0, and L sub 1, which we know is 0.8. So since P equals 0, this entire part of the equation equals 0, thus B equals 0.8. So in order to find the value of C, it's actually relatively easy. C equals 0 because the parabolic function passes through the origin, 0, 0, meaning its y-intercept, which is C, is 0. So now that we have all the numerical values for our parabolic function, we now have to find the y value, or the y-intercept value for L sub 2, because before we had L sub 2 equals negative 1.6 plus t. So we're going to find t now by basically setting the parabolic function equal to L sub 2 at point 100, because that's Q's x value, which the linear equation of L sub 2 passes through. So I'm going to do that right now. So we know that t equals 120, and that is where the linear equation of L sub 2 passes the y-axis, or intercepts the y-axis. So we found all of our unknown values. So here are 3 equations for our graph of our roller coaster.
We are finding the elevation from P to Q using Q's x value, 100, which we are going to plug into this f of x function. And we get the answer of negative 40. That doesn't seem like it would be a smooth ride because the piecewise function, L1 and L2, do not have a continuous function to make the ascent and descent run smoothly into the parabolic function.
The transition from the linear functions into the parabolic functions aren't smooth, so it's going to be a bumpy ride. And no one's going to ride a roller coaster!
And we need the money.
Well, what if we just add in 2 cubic functions?
That could work. If we put a cubic function coming into the linear here and a cubic function coming out of the linear here, it would make it smooth enough for the ascent and descent that people would want to ride it. We have to make sure the slope for the linear functions and the cubic functions are equal at the tangent points. And that is equal to the linear functions and the cubic functions are equal to the parabolic functions where they meet. We're going to do more calculus.
Okay, so the bounded interval for g of x is greater than or equal to 0, but less than or equal to 10. And this x value ends at 10 because at this point the cubic function is starting to descend, but we want it to smoothly transition into the parabola. And for h of x, the bounded interval is x is greater than 90, but less than or equal to 100. And this is because the second cubic function is starting to ascend, but we want it to smoothly transition into the linear equation. Okay, so we have 11 unknown variables that we need to solve for. And to do this, we took our handy-dandy computer engineer, Casey, and he plugged them into his computer algebra system that he has. And basically what that does is just put the variables and equations into big matrices. And we did this for each of the transition points, which is 0, 10, 90, and 100, and we took the equations that went along with that. So for example, at x equals 0, the 2 equations that go along with that transition point are L sub 1 and g of x. And so we plugged 0 in for those x values, and we got n equals 0. And then we plugged that into our matrices. So here's kind of a little example of what that computer algebra system did just for at x equals 0. And so we have matrix A, which is all of our coefficients for the equation. And then we times that by the variable equation, or the variable matrix C, excuse me. And then we have everything on the right side, which is matrix B. and that's equal to 0. So we took the inverse of matrix A times matrix B, and we came out with all of our numerical values. And we're doing this for the first derivative, the second derivative, and the original function. Okay, so we have our final graph for our roller coaster, and as you can see, the transitions are a lot smoother with the cubic functions that we put in with g of x and h of x. And also over on this side, we have all of our final equations for L sub 1, f of x, g of x, h of x, and L sub 2. So we're finally done with our roller coaster.